Okay, we should be recording. So welcome back. This is the first real lecture of the course, I guess. The last lecture is more of an introduction, so that's why it's lecture 0. But this is where we start getting into the actual details of machine learning, what it can do, what it can't do, and how to use it. So just some random administrative stuff. Homework 0 is out. Released that last week. You have 1 more week to do it. It's very simple. Just make sure Python is installed and things work correctly. So homework 0 should be trivial. That should take you 5 minutes. If it takes you more than 5 minutes, please let me know. So I'm happy to help debug installation things. That's usually one of the hardest things to fix, but I'm actually really good at that, so I'm happy to help with that. I've seen 6 people already submit. How many of you have submitted homework 0 already? Okay, 6 other random people, cool. So do try to do that just to make sure everything is installed and set up correctly, because that'll help with all the previous ones, all the future assignments. Homework 1, I just uploaded to Moodle, so it is out now. It's due in 2 weeks. And that'll be the first real homework where you actually have to write your own code and train a machine learning model to make predictions. And then the other thing, I mentioned this last week, I want to remind people, please no LLMs. You all have a free subscription to Atom GPT. Despite that, every semester I have at least 5 people who use ChatGPT for their homeworks. And every semester I have to fail 5 students. So please don't be that student. It's really easy to pass this course. Just don't cheat. So that's everything about the homework. The other thing that I wanted to say, especially for this lecture and one of the later lectures on deep learning, I'm going to show you a lot of the math, a lot of the theory behind these things. There are no math prerequisites for this course. You are not graded on your math abilities. If you understand the math, if you've taken things like linear algebra, probability, statistics, great. Knowing the math can help you do machine learning much more effectively. If you don't, that's also fine. We're mostly just taking built-in models from scikit-learn or PyTorch and using them. We're not designing them ourselves straight from the mathematics. So this is a very applied course. The homework, the final project, this is all coding-based. There are no exams. I'm not going to test you on your math knowledge. So don't panic when you see the math. What are we going to talk about today? So this is just a broad introduction to machine learning in general. All of the different types of machine learning, the different ways of classifying it, the ways that, the types of things that you can solve with machine learning. And then we're going to take a deep dive into several different machine learning models. Again, very superficial. Here's the model. Here's kind of how it works. Here's the pros and cons. Without getting into deep derivations, we're not going to prove convergence of any of these algorithms or anything like that. And at the end, I'll talk about the coding, which you'll need for your homework. So can anyone remember our definition of machine learning last week? How did we define machine learning? I think one of you told me the correct answer, so I don't know if that same person is here this week. What is machine learning? This should be easy.
Pattern prediction and analyzing the pattern using data set and then prediction.
Yep. So it's basically teaching a computer, teaching a machine to learn, to find patterns, pattern matching from examples, right? If you train it on a bunch of examples, it gets good at doing that thing. If you want to learn from example, the first thing you need is examples. You need data sets, exactly. So the first step of machine learning that people don't actually often think about is actually making your data set. The data set is oftentimes more work and more important than the model itself. I'm distinguishing between the words data and data set, so you can have infinitely many unlabeled data. There's plenty of data around you. Everything could be data. You could take 1,000,000 images of the Earth, and that would be data. But that's not the same as a data set. So a data set is collected for a specific purpose. It often has both input data, such as images or text, but also outputs, correct answers that you're supposed to learn. So the inputs, those are also called features. Those we will describe using the variable x. Anything that you can represent mathematically could be an input. It could be a simple number, but it could also be a complex number like an image. It could be text, anything that you want as input. Similarly, your output, which is also known as the target, that can be anything. It can be one single label. It can be a label for an entire image, every pixel. It could be a bounding box. It could be more text, anything that you can dream of, as long as it can be represented mathematically. What are some examples? Here we have an image, that's our X, and we have a label, cat. And you could have an entire data set of pictures like this with labels. That's something like ImageNet, where you've got 1 million different things of these. They're not all cats. There's 1,000 different possible objects in ImageNet. But that's a perfectly valid machine learning data set. It has a correct answer, and the goal is to train a model to go from an input image to the correct output label. Similarly, you could have text. And for example, it's one of the best movies I've seen in a long time. And the rating is 4.5 stars. And your goal is to train a model to understand language and predict, given this sentence, do they like it or do they not like it? So let's say we only have text and we don't have the stars. If you read this as a human, yeah, that sounds pretty good. But if I change it slightly and say, this movie isn't a waste of your time, you have to understand that the isn't negates the waste of time, and that's actually a good review. So there are grammar rules that you can learn from simple sentences to make correct predictions. So this is also a valid data set for text to score. Yep. Mathematically, we can write our data set using the following. So we got this little curly looking D, and then we've got a set, that's the curly braces. It contains n things, n examples, and every example is a tuple of both an x and a y. So every input has an expected output. There's not just 1,000 random inputs and 1,000 random outputs. They are matched with each other. That's a data set. This is actually only one type of data set. This is the simplest and most common data set where you have both an input and output. In machine learning speak, we would call this supervised learning. So there's different types of learning that we might want to do. The simplest one is supervised. So for all of these, we have the English text, we have the pictorial representation, and then there's a couple different math notations that you might see commonly. Basically, we want to learn a function f that if you take an x as input, it will give you the correct output y. That's it. We're mapping from x to y using the function f. Easy. Unfortunately, the vast majority of data on Earth does not have a y. So like if you think about something like satellite imagery, we've got about 100 petabytes of publicly available free satellite imagery, probably double that if you include commercial paid satellite imagery. So there's a lot of data out there. Less than 0.1% of that has a label, so most of it is just images, there's no labels. We can still do machine learning even without labels. We can do things like clustering or quantization. So I can say, here's all of my data X. Let's put them in buckets and say, here's 10 buckets where most of the inputs are similar. I don't know what these buckets are. Maybe they correspond to one specific class like cat or dog. Maybe they don't. Who knows? But I can cluster things, and that is one form of learning, and it can be useful for many tasks. Of course, we have supervised on one end of the spectrum and unsupervised on the other. There's a big blank space in the middle. There's all kinds of things in between these two distinctions. So for example, we have semi-supervised learning. Now there's several different kinds of this. It's also known as weakly supervised learning. The idea is, let's say you've got 1 million images, but only 1,000 of them have labels. You still have the other 999,000 images, but they don't have a label. Can you still use them to get better than only using 1,000? So can you assign pseudo labels using the data that you do know to train a better model in the end? Another place that this comes up very often in Earth observation is you have labels, but they're not like very detailed. So for example, you have images of the Earth and you've got a map, but the map is lower resolution. And you would like to train a model to make predictions at high resolution given a high resolution image. But the labels are really blurry, so you're trying to figure out how to take a real image and super resolve the labels, zoom in. Another place that this comes up is you have labels for everything, but the labels aren't very good. So for example, they were labeled by an amateur human, not a real scientist who knows what they're doing, or they were labeled by a simpler AI or machine learning algorithm, and you would like to train a more complex deep learning algorithm that does even better. So how do you get better performance than the labels on which it's taught? This is the true answer. So that's the area of research called semi-supervised or weakly supervised learning. And then the other category in the middle here is self-supervised learning. So with this idea, you don't have any labels, but you can make your own labels, right? So for instance, if I download every satellite image around that world, I don't have a label for every pixel, but I do have like the lat long of that image. So I can basically play a game like GeoGuessr, train a model to predict latitude and longitude given the image. And if it does well, it's certainly extracting some important information from the image. That might not be the actual task that I want it to do in the end. I might actually want to do it to make labels for things. But this is a very common pre-training stage for newer fancy things like foundation models. So in this course, we're going to be doing about 90% supervised because this is the most common application. This is the easiest and most intuitive application. But we will see a little bit of self-supervised. We have a lecture on foundation models, and we will also see a little bit of unsupervised in lecture today and on the homework next week. And feel free to explore any of these on your final projects. So I have had students explore both semi-supervised, self-supervised, and unsupervised learning in final projects. So that's perfectly fine to do. But we will be mostly focusing on supervised learning. For anyone who came in late, this is also a pretty good way to represent the previous slide. So supervised learning, they have like 1 million labels, easy, no problem. Semi-supervised only gets 1,000 of those labels and still has to somehow get a good prediction. Self-supervised is making their own labels, and then unsupervised is like, what is a label? I've never had this. This is useless to me. So this is the same thing without the math. The other way to think about machine learning, to categorize machine learning, is the different things that it can do with the outputs. So what tasks can a machine learning algorithm solve? The most basic tasks at the shortest, smallest level that we'll see today are things like regression. So this is when you want to predict a number. For example, what is the temperature tomorrow? That is a number, that is a floating point number. It could be positive, it could be negative. I wish it was negative because then I could get some snow, but I think most people would prefer it to be positive. Also depends if it's Fahrenheit or Celsius, because negative Fahrenheit's pretty cold. But that is a regression problem. You were trying to predict a number given your input data, which could be the past, today's weather. Predict tomorrow's weather given today's weather. That's a regression task. Another type is classification. This is where you're trying to categorize data. So for example, I showed you an image earlier where here's an image. This is an image of a cat. That is one classification problem. I could also show you a satellite image, and you can tell me, is this an image of an urban area, a forest, agriculture, etc.? So these are common tasks in supervised learning. You either predict a number or a category. Another type that's unsupervised, I already mentioned, is clustering. So here we don't have a correct output. All we're really trying to do is group together things that look similar. And there's other types as well that I'll go into more detail in later lectures. Most of the machine learning models we're going to see today, you can technically use them for all three of these things. Some of them are better at one or another, but they could all be adapted for all three. The ones that I've shown you so far, regression, classification, clustering, these are for one single input, but you can also have a corollary of this at the image level. So for example, if you want to do regression on every pixel in an image, that's pixel-wise regression. If you want to do classification on every pixel in an image, that's semantic segmentation. You are trying to take an image and segment it into different semantic classes. Similarly, you can do clustering on pixels and do things like quantization or dimensionality reduction to shorten the file size. You can technically use these old school machine learning models to do any of these things. Usually deep learning does better on image level, high dimensional stuff, only if you have enough data. So a lot of people ask me like, why teach machine learning when everything is deep learning now? And it's because you rarely have enough data to do deep learning. That's changing with foundation models and self-supervised learning. It is now easier to use a smaller amount of data and still get good results. But machine learning can be used in a lot of situations where you can't pre-train a model or where the data is just very limited with labels. I don't know if I have a slide on this. People always ask me like, what does big mean for data sets? Like how much data is enough data? And it really, really depends. For classical machine learning stuff, some of this will work with 10 or 100 examples. With deep learning, if you're training something from scratch, ideally you'd have like 1 million examples, but maybe you could get away with only 1,000. So that's kind of the scope of what I mean by big versus small data sets. If you've got less than 1,000, probably want to use something like classical machine learning. If you got more than 1,000, try deep learning, it might work well. Okay, so the first class of machine learning models that I want to talk about within the supervised space are known as non-parametric models. Parametric, that just means parameter. So non-parametric models, actually despite their name, may or may not actually have parameters. But usually, the number of parameters grows with the data set size. So if you have a huge, huge data set, you also have a lot of parameters in your non-parametric model. The downside of these models is that they usually require a lot of data to do well. But the pro is that they're very, very flexible. So no matter what data you give it, it will work, and it can be mathematically proven that it will work with some guaranteed levels of accuracy. So let's start with a real example, a real machine learning model. What's the simplest thing you can think of given examples and you want to learn to mimic the examples? Well, if two inputs look similar, then the outputs should also be similar. So I just look for the most similar input, and whatever its label is the right output. This is known as nearest neighbors. There's no real learning process. You're actually just memorizing the entire training data, and it tends to get much better performance the more examples you give it. Mathematically, we can represent it like so. So again, I is the number of my data, 1 through n. For a new x, I look for every single x within the original data set. So all of my example data with labels, and I find the one that's closest or most similar. There's a lot of different definitions of similarity within mathematics. Here I'm just using a 2 norm. So this is Euclidean distance, something like x1 squared plus x2 squared square root. And I can add a little squared at the top to get rid of that square root, so that's less math to do. The result is the same. So it's basically x1 squared plus x2 squared. So I look for the input x from my training data set that is most similar to my new input x. And then whatever the label is for that one, that's my prediction. If you take all of your examples and you plot them on a map, you get something that looks like this. This is called a Voronoi diagram. And basically what you see is all of these points are real data points within the training set. and they're on some axis, x1, x2. This example is 2D. It doesn't have to be, it could be 1000D. The exact math still works, right? So I'm doing 2D for visualization. And if you give me a new data point, for example, here, I'm going to say, well, its nearest neighbor is down here, and that one's blue. This is probably also blue, right? So very, very simple, very intuitive. It does not make any assumptions about how the data is distributed. It doesn't have to be linearly separable. It doesn't have to be a nice Gaussian distribution. Whatever data you give it, it will make a prediction, and it's sometimes pretty good. You'll also notice that it's not perfect. It's sometimes very noisy. So for example, if I get a new data point right here, technically its nearest neighbor is this one. So it would classify it as red. But realistically, it's probably blue, right? Everything else around it is blue. This is probably just noise. So this isn't the best method, but it is very flexible. It is very simple. So what are some disadvantages of this method? I mentioned this already. I have to store the entire data set in memory. And we know that these models are very data hungry. So if I want to get good results, I need a lot of data. So I might also need a lot of memory. So that's not great. Training, I don't have to do that at all. It's instant. I just have to memorize the data. When I want to make a prediction, I have to loop over every single example in the data set to find the one that's most similar. Maybe we can parallelize that, but it's still going to be quite expensive, especially if you have a lot of data. And then I already showed this on the previous page. The predictions are quite noisy because of the inherent nature of nearest neighbors. So there's a couple extensions of this method that can get you better results. The most common one is k nearest neighbors. So I don't think anyone actually uses nearest neighbors on their own. Usually people use something like k nearest neighbors. So what is k nearest neighbors? So let's say I have this new point in the center in green. If I look at the nearest neighbor of this point, it's this, it's red. So I would predict this as probably also red. If I look a little bit farther than just the one nearest neighbor, I can look at the nearest three neighbors. And I can say within this radius, 2 out of 3 are red, so it's still red. But if I look at k equals 5 and I go even farther zoomed out, all of a sudden, well, 3 out of 5 are blue. Maybe this is more likely to be blue, and then these are both outliers. So depending on how much you expect there to be outliers versus how clean you think the data might be, you might want to choose different values of k. If we're doing binary classification, great. We pick an odd number of k, and then one of the two classes always has more examples. Easy. How would I do this for multiple classes? And I'll let someone suggest something. There's no right answer. There's many different ways to do it. But how would you do this for, maybe there's 3 different colors you're trying to predict?
Try and check all possible k values.
Okay, so you want to try multiple different values of k. How do you decide which one is right? Okay, so your idea is we can try several different values of k. Some of them will have a tie, but some of them won't have a tie, so we're okay. And as long as they're within some range that makes sense and the results visually look good, we're good, right? That works if the results are easy to interpret. So in this example in 2D, I've got an image, great, very easy to see. If this is 1,000 dimensional hyperspace, no chance of visualizing this. So I have to rely on other tricks like how far are things, what is the average distance between points and the certain number of nearest neighbors. There are ways to do that. You can also just do the simpler thing and say, flip a coin. Every time there's a tie, randomly flip a coin. And then we won't end up with bias in any direction or another. We will get an answer. It's maybe right, it's maybe not. It's a tie, who knows? It's 50% this, 50% that. If you make me pick one, it doesn't really matter how I do it, as long as I do give you one answer in the end. So there's several different tricks for doing multi-class for this. But the formulation I've shown you so far, this is mostly for this binary place where there's only two possible values. Similar question, how would I use this for regression? I'm showing you classification. Things are either blue or red. How would I do this for regression? Let's say these are weather stations or air pollution sensors, and they each have a measurement of temperature or humidity or CO2 or nitrous dioxide. And I want to know what the expected value is in the center. How would I use something like k-nearest neighbors for that? Yep. Yep, that's perfectly valid. So I can choose my k, and I can take the median, and that will be much better if there's outliers. I can take the mean, and that weighs all of them equally, but it's more susceptible to outliers. I can also do the weighted mean. So for example, two of these stations are much closer than one of them. Maybe those influence that value more. So there's several different ways that you can do k-nearest neighbors for regression. I think weighted is a good one, but that doesn't mean that it's always the best. It depends on how much there are for outliers. Maybe you have to clip outliers. You do like the k equals 10, but you remove the highest and lowest is another completely valid approach. In machine learning, there's rarely one right solution. There's several solutions, and you have to try all of them and see which one works best. But of course, there's assumptions you can make. Certain models tend to work better on certain applications. Another idea, we mentioned that nearest neighbors sucks because we have to store the entire data set in memory. It's huge, right? Can we get away with fewer parameters? What if instead of storing every data point, we store a smaller subset and form rule-based decisions? So something like the decision tree on the right, where given your age, given whether or not you smoke, given your weight, given various other factors, you can see what your risk is for a certain medical condition. You can do the exact same thing for satellite imagery, and I'll show a slide in a second. So what are we learning here? There's two ways to do this. I could either type in the number myself. I know that people under the age of 18 have a low risk of heart disease. Or I could learn it. So if you're trying to learn your decision tree, then you would specify things like the depth of the tree. Is it allowed for certain branches to be shorter than others? Is there a minimum, maximum, or are they always all the same length? You can have a width. So you see at the top here, that first node has 3 different options. I could force it to only have 2, or I could say it has 10 possible categories. I don't have to use age only once. I could put age again down there and have a smaller subset. So there's many different ways to learn this tree, but it can be learned based on real examples, real data. So both the nodes, what thing we're measuring, and the values, those transition values, those can both be learned during the training process. Again, we can also use this for regression. Sometimes this works really well, sometimes it doesn't work very well. This is an example where it doesn't work well, and what you basically see happening is we have an underlying function that's generating our data. It looks sinusoidal, right? If it's 2D, easy. We know it looks sinusoidal, we can plot it. If it's 1,000 dimensions, I don't know that it's sinusoidal. I can't know that it's sinusoidal. I have to learn it. Decision trees are good at learning these kind of rule-based decision boundaries where everything on this side is one value, everything on that side is another value. You can have a lot of different sections, but it's very easy for it to overfit to certain outliers because it's basically trying to fit the entire data set as best it can. You'll notice that some points don't get perfectly fit. We limited the tree depth and tree width. So it's doing the best it can with how many parameters it's allowed to learn and making the best fit that it can. So this is an example where we probably shouldn't use a decision tree, but we can. There are other examples where decision trees work better for regression. How many of you are engineers? Raise your hand. So if you're an engineer, you probably shouldn't be in my class. This is really all you need to know. So if it's supposed to move and it doesn't, then use WD-40, and other way, use duct tape, and that's most of engineering. Obviously, there's a little bit more details when you get to the college level, but that's a pretty good summary. But this is a decision tree. So decision trees are nice because they're very simple. You have a very small number of parameters. They're intuitive, they make sense to humans. We see stuff like this all the time. We know what a decision tree is, even if we've never heard that specific name. But they tend to overfit really strongly. So they'll hyper-focus on one specific outlier and change the whole model just to fit that outlier. That's not something we really want. So what can we do to make our decision tree more flexible? Well, why not use many trees? So this is a method known as random forest. Forest because there's many trees. Random because each tree is fit to or trained on a subset of the data, a random subset. So some trees see that outlier. Other trees don't see that outlier. Most trees don't see that outlier. And when you average all of their predictions together, the outlier disappears. So basically you do a majority vote or an average if you're doing regression on all of the decision trees that you use to make your prediction. This is actually a large family of models called ensembles. This idea is quite common in machine learning. So there's things like bagging and boosting where you start with one tree and then you find the examples where it doesn't work well, and then you train a new tree only on those examples, etc. So there's different tricks that you can do with a bunch of small, simple, stupid models that are combined together to make one intelligent prediction. If you've ever looked at a weather forecast, those are ensembles. If I take one physics model or machine learning model for predicting weather, if I perfectly know everything about the world to the resolution of a single atom, I know where every molecule of oxygen is, every molecule of water, the wind speed of every molecule, then yes, I can maybe predict the weather a week from now perfectly. But I don't know everything, and we also have this thing called chaos theory, where even if you know everything, the atmosphere does weird things that can't be easily predicted. So what you can do instead is, if you've got a bunch of weather models that are pretty good, but they don't really have the detail you need to make perfect predictions, you can make it, the same model, make 100 predictions and take the average. And that's the weather forecast. That's exactly how they do it, both with physics models or machine learning models. I mentioned that I would show an example of this. So this is that decision tree on satellite imagery. If you remember from lecture 0, I talked about thresholding, where I said, oh, you can take your image, you can make it grayscale. Everything that's a big number is cloud, everything that's a small number is not cloud. Easy. But in reality, we've got a lot more classes than that, and grayscale isn't going to cut it. Different spectral bands, different color channels of your satellite image might tell you very different things. So this is an example decision tree where I can look at, for example, band 4, which I believe is, I don't know if this is from a real satellite or not. Let's pretend it's blue. So if things have, well, no, that wouldn't make sense if it's a small blue. If it's Sentinel-2, then it'd probably be red. So let's assume band 4 is red. If it's not very red, it's probably water. If it is even a little bit red, it's probably something else. So water strongly absorbs the red spectrum, probably. I don't actually know. Therefore, we go down the other side of the tree. And then we look at band 3, which is maybe green. And we say if green is a large number, it's actually more likely to be a cloud than anything else, because real green doesn't reflect that strongly compared to the other colors. So then we go down the other tree and we check even smaller values, and then get even more finely detailed different amounts of green that could be different categories. And you eventually get a map that looks like this. It's very noisy, there's a lot of mistakes, but it's not bad, it's not awful, it's a very good place to start. So this is a decision tree based land cover mapping application. This would be useful for a lot of different agencies who are doing things like mapping deforestation, mapping water resources, whether or not lakes are shrinking or rivers are overflowing, flood mapping, earthquake damage mapping. A lot of different applications require you to do semantic segmentation, classification of every pixel in an image. Are there any questions on this, these non-parametric models? Everyone is very quiet today. So those are our simple non-parametric models. They're very flexible, they work with any data, but they require a lot of data to make them work well. The other category of supervised learning models are parametric. These are models where we are learning a set of parameters that describe the system overall. For example, I could look at all of you and say, if I only cared about your height, there would be some mean height and a standard distribution, and everyone fits some sort of Gaussian height distribution. Not all natural phenomena have Gaussian distributions, so that doesn't always work, but a lot do. So these models make assumptions about the underlying data distribution. Most of them require the data to be Gaussian distributed approximately. There's a specific acronym that you might see used time from time, IID, that stands for independent and identically distributed. What that means is if I have a data set of 1,000 people, and I add one more person to my data set, their height, their age, their features would be independent of the ones that I've already sampled. So it's not like a time series, for instance, where the weather yesterday is very relevant to the weather today, whereas the weather a month ago is not relevant to the weather today. So time series would not be independently distributed. You can still use these machine learning models for non-independent data. They just might not work very well. The other important thing with parametric models, fewer parameters, but also less data. So we can represent a very large high-dimensional space with a lot less parameters than you would need for a non-parametric model. You've actually done, most likely, parametric supervised learning before. If you've ever heard of something called ordinary least squares, just making a line of best fit. This doesn't sound like machine learning, but let me explain to you what I mean. So I've got data on the right. For every value of x, I have some value of y. If I learn the function in blue that fits that data as best as possible, I've now learned a function that given an x, I can predict what the y is going to be. It's the value on the line. And most of the time it's pretty close. So we've learned from examples, we've got a bunch of data points, and we've learned a function that predicts what the y is given the x. So this is a form of machine learning. This is one of the simplest machine learning models. So I have linear in quotes. What do I mean by linear? So you're probably used to a linear equation looking something like this. F of x equals ax plus b, or y equals mx plus b, or whatever. This is a linear equation. What if I change this to something like ax squared plus bx plus c? Is that linear? I'm seeing a lot of no's. It is not linear with respect to x, because it's a parabola, right? Just like in the image on the right. It is linear with respect to a, b, and c. So this is a very different type of math than you're used to. We actually don't care about the x or the y. We have the x and the y. We want to learn the a, the b, the c. We want to learn the parameters of our model. So we're learning the slope, the y-intercept, or if you have a parabola, the curvature of that parabola. So that line on the right, that blue line, that's not a straight line, but it is a linear function. It is linear with respect to its parameters. So you can do any kind of equation you want as long as it's linear with respect to A, B, C, whatever. And on your homework assignment this week, you'll actually be doing linear regression with a sinusoid. You can do linear regression on that, of course, as long as it's linear with respect to the parameters A and B. How many of you have taken linear algebra? You've seen vectors and matrices and stuff like that. I'm seeing a couple hands and a couple nods. Okay. If you haven't, turn off your brain for 5 minutes. If you have, continue. So the first line here, this is the one-dimensional, this is the zero-dimensional version of this equation. My x is a scalar, it's just a number, and my output y, or f of x, that's also a scalar, it's just a number. What if my input x is a vector? For example, x1, x2, x3, maybe it's a vector in three-dimensional space. Now my x becomes bold, that's my vector notation, and I will have many different parameters, a, b, c, for that x. I'm going to rename these w, and this is my weight. But these are still the parameters of the model. Parameters, weights, these are the same word, these are synonyms. If I do a dot product between my weight vector and my x vector, and maybe add some bias at the end, they still have that y-intercept thing, I can make a new prediction for y. So this would be the one-dimensional version of the exact same equation. Now we can work not only with one input, but any number of inputs. Now I also mentioned that I have a whole data set. I've got n different pairs of x and y. I'm going to take all of those and I'm going to stack those into matrices. So I've got one long vector for all of my y values, all of the correct answers. I'm laying all of my x's on their side, and I'm putting all of my w's in one vector. Now this next step is optional. You can move that w2 into that w1 as one big vector, as long as you just add an extra 1 at the end. And the end result is that we can represent the entire data set in any one-dimensional space using the simple vector form y equals xw. And the w and the x swapping, that's really just a result of the way that matrix multiplication changes dimensions. So you can do the math and see how the dimensions work, but it does result in something that is of dimension w, which is your y. Okay, so we went from this function up top, f of x equals ax plus b. We wrote it in vector and matrix notation. It's the same thing, but now it represents the entire data set for any number of dimensions. How do we learn, or how do we calculate the best line of fit? So if you've ever done this in Excel, this is actually what it's doing behind the scenes. Our goal, our objective, is to minimize the mistakes we make. So if you look at the image on the right, for every input x, if I predict a value of y on the line, those little dashed lines are the amount of mistake that I make. It's not the distance from a point to a line diagonally, it's directly up and down. So in this case, y is my correct answer. Y hat is my prediction. And the goal is to make these as close as possible. If I want them to be close, I minimize the distance, so I'm using a 2-norm, Euclidean distance, and I can square it because I don't care about the squared. It makes the math easier. And again, 1/2, why not? Doesn't change the math. So that's added because when you do the next step, you'll see why. So the goal is to learn a w, a set of weights, from whatever d+1 dimensional space that minimize this function. What is y hat? Well, it's xw. We saw that on the previous slide. So the goal is that the y predicted by xw is as close as possible to the real y. This is going way back to your first calculus course. How do I optimize something? Any function, I want to find the optimum value of that function, the minima, the maxima. How do I do that? Somebody here remembers. This is like high school calculus. Derivative. And what do you do next?
Find like where it's equal to 0.
Yep, exactly. If we're in n-dimensional space or d-dimensional space, instead of derivative, we have gradient. But exact same thing that you did way back when in high school, and you thought, this is so stupid, when will I ever use this? Every single thing in machine learning, deep learning, every billion-dollar tech company, everything they do is derivatives, set it equal to 0. That's it. That's the whole course. So that's the secret, right? Everything is actually just gradients behind the scenes. So in this case, let's do that. Let's take the derivative. Now, this is where you have to put on your thinking caps and probably get out pen and paper and spend like a good hour doing all of this. But if you take this 2-norm thing and you write it out in square root of x squared, x1 squared plus x2 squared, blah, 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 and you take the derivative of this with respect to each of the inputs, what you find is that the 2, the squared, goes to the front, cancels out the 1/2, and then you have the thing inside to the power of 1, which is just the thing inside, times the derivative of the thing inside, which is just x. We're taking the derivative with respect to w. We don't care about x, we know x. We want to learn w, we want to find the optimal w. So we take the derivative of this with respect to w, and we get the thing inside times x. I've also switched notation here. I had w here before, any w. W star, w asterisk, this is the optimal value for w. So now we're setting it equal to 0. The w star is where this equation is true, where this thing on the left will equal 0. I can multiply things through, subtract to the other side, and I can do an inverse multiplication, matrix multiplication, and get w star on its own. So basically, no matter what data you give XL, if it knows the x and it knows the y, it can run this quick mathematical equation and instantly tell you the line of best fit. Here is all the slopes in any dimensional space and the y-intercept. That's all it is, very simple. Now, I mentioned that all of these models can be used for regression, classification, clustering, whatever you want. This model is called linear regression. Can I use this for classification? Sure, why not? So if I wanted to change this, let's say I'm trying to predict y values and they're either -1 or +1, I can take my formula, wx plus w2 or xw, whatever you want, any of those representations we previously saw, and I can add a sign function, which converts it to either +1 or -1, depending on if it's greater than 0 or less than 0. What happens if it equals 0? What would you do if you got an input that equaled 0? 0 is not allowed, right? Again, it doesn't matter, right? It's almost never going to happen. And when it does, flip a coin. Just put it in positive or negative. It's 1 out of a million, who cares? Most floating point values are going to be some small number that is slightly positive or negative. It doesn't matter that much. So we've got our machine learning function. We can now classify things as either class A or B, positive or negative. Unfortunately, in practice, it doesn't work very well, and this is a good illustration of why. So in this case, we have 2 clusters. There's a bunch of things that are negative in blue. There's a bunch of things that are positive in black. And they all have x values. So if I do a line of best fit to this data, everything that is positive is correctly classified, everything that is negative is also correctly classified. If I do the same thing over here, my line shifts because of these outliers way over to the right. And so as a result, some of these black pixels are incorrectly classified as being negative on this side of the x-intercept. So linear regression, you can use it for classification. It's just not good because the line gets biased by the data points. What can we do instead? Don't use a linear function, use a logistic function. So this is a broad class of families, a broad family of functions where things kind of look like an S shape. That's it. So anything from a sharp step or Heaviside function to a smooth logistic function or a hyperbolic function, tan H is an example, something that looks like this. Now this function, even if there's points on both sides, it will usually fit them such that the decision boundary is right in the middle between the two groups, and it works much better for classification. Again, we've got some math here. We've got this long function. Now, I mentioned how do we optimize this function? We take the derivative. What's the derivative of a logarithm? I actually don't remember. I think it's another logarithm, but someone can correct me if I'm wrong. Basically, the point that I want to make here is if I do the math, if I take the gradient or the derivative, I set it equal to 0, and I try to solve that system of equations, it doesn't have an analytic solution. We can't just know the optimal value of W for the data. This is a very simple function. I know it looks complex. I promise things are going to get much more complicated in the second half of the semester. This is a relatively simple function. It's 1 plus e to the negative x with a logarithm. How hard could it be? But this can't be solved. That's not good. So thinking way back to calculus, and this is something where you might not have learned in calculus, but maybe you learned in a later engineering course. What do we do if we can't solve for 0? What is another approach for minimizing something, optimizing something? I can't calculate when it's 0, but I can calculate it, and I can go downhill. So let's say this function you see here represents the amount of mistake that we make. There's two axes, W1 and W2. These are the parameters of my model. And then the vertical axis is the amount of error, the amount of mistake. So I pick a random starting point, and I calculate the gradient. Now I can't calculate where the gradient is 0, but I can calculate what the gradient is, given a specific W1, W2. If I know the gradient, I know which direction is downhill. My goal is to minimize my mistake, right? So I just keep going downhill until I stop. And that's known as gradient descent. So here I would pick random point up here, and I would say downhill is this way. And I would go a certain distance. I won't tell you how to figure out the distance, but a certain distance. And I find a new point. I calculate the gradient. Oh, downhill is now this way. I jump over here. And I just repeat this process until eventually I stop. Eventually I converge. Knowing the optimal value for this is actually really challenging. There's a lot of research that goes into knowing how far do you jump before you stop and try again. You'll notice here that the first couple of jumps are very big, and then eventually we start going a smaller distance. If we keep going a big distance, we'll never stop, right? But if we eventually slow down, we will stop somewhere, and it will hopefully be a good minima. With all of the functions that we've seen so far with linear regression, with logistic regression, these are known as convex functions, where our surface only has one local minima. If you keep going downhill, you will get to the global minima, the optimal value. The second half of the course, where we get into deep learning, there's infinitely many local minima, and you have to hope that your local minima is good. But for now, this will be quite simple. Just go downhill, stop. That's a good value. I want to go back to classification. I keep showing you ways to do binary classification, and I keep avoiding the question of multi-class classification. So now there's not just red and blue, there's 10 different colors, and you have to pick one. All of the functions I've shown you, I've basically just said, is this positive or negative? Class 1, class 2. How do I do multi-class classification? There's two strategies that are quite commonly used for these classical machine learning models. One is 1 versus 1. So you train a model that decides, is this red or is this blue? You train another model that decides, is this red or is this green? You train a third model that says, is this blue or is this green? And then you make predictions with all three of them, and you see which one is the majority vote. You don't have to do 1 versus 1. You can also do 1 versus rest. Is this red or is this not red? Is this blue or is this not blue? Is this green or is this not green? Now, I want to show a quick YouTube video to explain this that I really love because it explains this problem so well. This is, how many of you have seen a comedy show called Silicon Valley? Anybody? Oh man, I feel old now. So Silicon Valley is, as you would expect, a comedy show about startups, startup culture in general. And there's a bunch of people who work at a incubator. So there's a tech giant who's incubating all these cool ideas. And if someone makes the next big Google or Apple, then he gets a bunch of money back from sponsoring him. So this is Jimmy Wang in Silicon Valley explaining 1 versus rest classifiers. And I think I figured out the audio this year.
Please, God.
What will you say if I told you there is an app on the map?
Past that part. Just demo it.
Okay, let's start with a hot dog.
Holy shit! What the fuck? Huzzah! Jin Yang, my beautiful little Asiatic friend, I'm going to buy you the palapa of your life. We will have 12 posts, braided palm leaves. You'll never feel exposed again.
I'm gonna be rich. Fuck you, Guilfoyle. Do pizza.
Let's do pizza.
Yeah.
Pizza.
Not hot dog?
Wait, what the fuck?
And
That's it? It only does hot dogs?
no, and a not hot dog.
Did you? Jin Yang?
So the point here, and this seems silly now in the age of AI, where that kind of app is already on the market and it works great. If you go back 10, 20 years ago, taking an image in any random light conditions with any random centering location, with different condiments, different other things, it'd be almost impossible for you to design an algorithm that can simply classify that as hot dog or not hot dog. But if you can do hot dog or not hot dog, you can also do pizza or not pizza, and something for every category. And then all of a sudden, you can build a very large and powerful multi-class classifier. So this is the way that classical machine learning solved the multi-class problem. When we get to deep learning, we'll see a much better solution, but this is something worth knowing about. One last parametric model I want to get to before we take a quick break. So you might, if you know anything about the history of machine learning and deep learning, et cetera, a lot of this classical machine learning stuff that you're seeing here, this is from the 1950s, the 1960s, 1970s. We've had these ideas for a very long time. They're very simple and powerful. You don't need a very powerful computer to quickly calculate a straight line or something like that. So these work quite well. Sometime around the 1970s, we came up with this idea for deep learning. We said, if this works well, why don't we try this? And we tried it and it didn't work well. Because we didn't know what we were doing. We didn't have the right architectures, algorithms. We didn't have enough data. It needs a lot of data. We didn't have GPUs. So we didn't have anything powerful enough to do all of this stuff. So after the 1970s, after we had actually invented deep learning, around the 80s and 90s, we came up with a better way to do the original stuff, a better classical machine learning algorithm that still worked on these very simple computers and was essentially state-of-the-art until deep learning eventually caught up. So this is really the most powerful classifier that you could invent without getting deep into deep learning. So let's go back to our example of binary classification. I've got two different classes, black and white. I would like to learn a function that separates these two classes. What function should I choose? Well, there's infinitely many straight lines depending on the slope and y-intercept. H1, definitely not a good idea because it's messing up some of the black pixels. But H2 and H3 are both perfect, right? They both perfectly separate all of the data. Which one is better? There's in fact infinitely many within that small range that will perfectly separate these. I could also do a horizontal line or anything in between. Which is better, H2 or H3, and why? Exactly. So if I get a new point and it's right nearby one of these points, but it's right on the line, is it black? Is it white? I don't know. I've never seen anything here before. So if you pick H3, you've got the maximum possible distance between both sets. So you don't have to worry so much about those outliers. It's much less common to find something exactly on H3 versus much closer to those two clusters. So H3, we can say, is mathematically or provably better. How do we define H3? We use something called a support vector machine. So again, the idea is to maximize the margin or the distance between these two groups. We want a straight line that puts as much distance as possible between the two classes. The points that are on those little boundary lines, those are known as support vectors. So that's where it gets the name support vector machine. And again, this can be used for classification or regression. There's a little bit of math here. So if you've got your line, W times X, that's the dot product, minus B, that's our y-intercept. 0, that's the location of the optimal boundary. And our goal is to learn W such that this is true. If I add 1 or -1, I end up with the two support vectors. And then the distance between them is 2 over the 2 norm of my weight. So how do I optimize this? I maximize that. How do I maximize? Negative minimize. How do I minimize? Gradient descent. Easy. So if you ever hear a question in this course and you don't know the answer, 50% of the time the correct answer is probably gradient descent. It's secretly all gradient descent underneath the hood. It's really just the stuff on top of it, the types of functions that we use that changes. It's not the math. The math is always gradient descent. That's not technically true, but it's like 99% true. This is a best case scenario, right? All of the blue are on one side, all the green are on another side. These classes are linearly separable. A straight line is sufficient to divide these two. What if that's not the case? This math no longer works, right? So there's various extensions of this that allow for a certain number of points to be misclassified. Another way that you can do this is you can change your line. So instead of a straight line, I can use a curved line. What's the optimal curved line that fits all of the data and separates it? Well, that's actually much harder to do than it sounds. We need to learn some sort of non-straight line. It can be any arbitrary shape. What we can do instead is we can use something called a kernel to transform the original data to a different multidimensional space. And in this new space, things just so happen to be perfectly linearly separable. So this is actually how SVMs work most of the time. You're not learning a curvy line, you're learning a transformation, and you're learning a straight line after the transformation. What kernels do we use? Well, linear is the simplest one. That just gets us back to this slide. So you can do that with no transformation. You can do any arbitrary polynomial or sigmoid, but the most popular one, the best default that you almost always see people using is this RBF radial basis function. I can't remember the exact math of it. It doesn't really matter. The point is that it, a very large percentage of the time, happens to translate the data to a new space where things happen to be usually separable, but not always. So you still have to allow for misclassifications. Are there any other questions on any of this supervised learning, non-parametric or parametric? Cool. Let's take a 10-minute break because I know it's a long 2 hours. It's like 4:05 now, so we'll restart at 4:15. We'll wrap up with unsupervised, like clustering, and then we'll show the homework assignment. And then we should be perfectly on time. I got an email from Izdihar. Is that anyone here? Faradina. He emailed me looking for the room, but he couldn't find his way in.
So I have a bibliotheque elective course in main campus, so I need to leave. But I really like the course. And
Yeah, the lectures are up on YouTube. I'm happy you came all the way here, even though you have to leave early. You're definitely welcome to continue coming for the first half, but if it's like a lot of travel for only an hour, it feels bad. But it is up on YouTube too, so you can watch the second half of the lecture on YouTube.
Okay. And my house is really close to here, so it's
Okay, perfect. Then yeah, it's on the way basically. Yeah. Okay, cool. Yep. See you. I used to teach a course in main campus at 8 a.m. and I live here in Otterbrunn. So I'd have to wake up at like 6 a.m., quickly eat breakfast, get ready, and then get on a train before 7 so I could make it to campus by 8. And then by the time class was over, especially during the winter semester, it's still dark outside. By the time class is over, and I'm like, this is not realistic. This is stupid. So I finally fought back and got a late lecture.
I'm in the same course.
Cool. Yep, see ya.
What is the course switch between here and the main campus?
So the course I'm talking about that was at 8 a.m. is the image processing course. I taught that like 2-3 years ago. And then this course actually also does switch back and forth between here and main campus. So if Ottobrunn is like way out of the way for you and this sucks, you could technically take it next semester instead. The idea is that my office is here and my home is here. So this is great for me. And there are at least some aerospace students who come here anyway for a lot of lectures. So we try to go back and forth every semester.
It's fine for me. I don't live too far from here. But
Especially, I think it was last Tuesday, there's like no train. So like for some people maybe it's okay, but for a lot of people there was no one who could make it to the Tuesday lecture for a different course that I'm in. I don't know if I've ever seen the police in Ottobrunn. It's normally so quiet here.
Airbus is their own fire truck, correct?
Hmm?
Airbus is their own.
Oh yeah, they do. Yeah, I forgot about that.
Saw one in front of the building.
Yeah. True.
Maybe they were police.
There's also there's someone who lives near my house and I think he like works for the fire department, so he's got like one little vehicle just for himself. But the police, like what is going on in Ottobrunn of all places?
Somebody breaking into a high security facility.
Maybe. But they all have their own security force anyway.
Good handle.
We did have that arson last year. Does anyone remember that? There was an arson attack here last year where all the cars and vans behind this building got burned to the ground. And I don't think they ever caught the person. Such a weird thing. I'd never expect any crime to happen here.
Maybe somebody got fired.
Yeah. I think that's the leading theory. Where did you get an ISA t-shirt? And where do I get one?
I got it during a student rocketry competition in Portugal. But
So I just need to build a rocket and go to
I
Portugal.
can also tell you from experience, I also got one from Gamescom. So
Okay.
they are in a few different places.
Okay. Yeah, I want one. They're pretty cool. I also want a NASA t-shirt. I don't have a NASA t-shirt, but those like you can buy those anywhere you want. Those are pretty
I think
popular.
There's an ESA shop.
Yeah.
Already up there. You can also get
Maybe I should give them money. They've given me so much free data. I feel like I deserve to give them money. I think I can give them 10 euros for a t-shirt with a billions of dollars worth of data they've given me. All right. So let's keep going. So we've seen the supervised side of things. We saw the parametric and non-parametric models. What about the unsupervised side? What do we do if we don't have any labels? Can we still learn some sort of useful information from that? This is another model that you might have heard of before. It's quite common, even outside of machine learning, but it's k-means. So the situation is lots of data, no labels. We want to find structure. We want to find clusters. We want to find patterns. We can cluster our data, basically take the full data set and partition it. And it's the same idea we saw before with nearest neighbors. Similar data, same cluster. Different data, different cluster. Easy. I do want to be clear, though, that k-means is not k-nearest neighbors. These are very different things. So with k-nearest neighbors, we have the answer, we have the output label. We look for nearby points to find what the label should be. Whereas with k-means, we're not storing the entire data set in memory. We have a small number of exemplars, basically cluster centroids that everything else is compared to. Both of them use hard clustering, which means that one point can either be in one cluster or another, but not both. We will see an example later where it's soft clustering. A point can be in two clusters. Again, I can do that same Voronoi diagram that we saw earlier, but now instead of doing a different little cell for every point, I have a much smaller number of cluster centroids. And then every point in that space belongs to one centroid or a different centroid. Now this specific data set, the clusters are kind of all over the place. It's not really clear where the boundaries are between them, but we can fit the most dense locations and put a little white X there. There's actually two different styles of doing k-means. Either your X is a real data point, so one of your many data points becomes a cluster centroid, or it's literally just a location where the points mostly are. It doesn't have to correspond to a real data point anymore. What does the math look like? So our goal is to learn a certain number of clusters, k, that's the k-means. We will describe those centroids using mu. So that's our mean, basically. Now, every point x belongs to one of those k clusters. So basically, the j that minimizes this equation, so your new point being close to cluster j, for all possible points, for all possible clusters, that is the objective. We want to minimize the distance. So all points belong to the nearest cluster. There is an algorithm to solve this called Lloyd's algorithm. It is quite simple. First, choose k starting points and do two things. Recenter it. So all of our points are in a cluster. Let's find a new center right in the middle of this cluster. And then let's reassign. So we'll take all of the points for the full data set and put them in the closest cluster. We repeat those two things until nothing changes, and that's it. What does this look like? Looks like this. So our starting clusters, we've got two pretty far in the top. Those are those black stars. We've got one in the middle of nowhere down here. If I do these two steps, and I say, okay, all these points are in this cluster, what's the middle of this cluster? Make a new star. And then with all these new stars, what points belong in that cluster? And then make the cluster bigger. So you can see that the huge number of points in this area that start off all as green, that one actually gets pulled by this more dense cluster. The blue area gets pulled to the middle of this cluster, and the orange one stays right in the middle of this cluster. So if the data looks very nice, if there's these three obvious easy clusters, this works quite well. There's a bunch of problems with k-means. It's really sensitive to this. Choose k initial clusters. If I choose the wrong starting points, this blows up. This doesn't work very well. So usually, when we pick a starting point, we pick it randomly. There's a couple different ways to pick it randomly better. This is known as k-means plus plus. So instead of just picking 3 random points, I can pick 3 points that are kind of far apart from each other. They're not too close. That's it. Something simple like that. Or instead of picking a point where there is known data, I can pick something within the broad area of all data, not just one existing point. So there are ways to solve this first problem, but in general, k-means is very sensitive to the starting position of your clusters. If you run k-means 10 times, you'll hopefully get the same answer 9 out of 10 times. 1 out of 10 times, you're going to get something completely different, and it's not going to be very good. So a lot of people who use k-means will actually run it 10 times and then choose whatever's most common. Those are the best clusters. So that's not great. That's a problem. Also, each point only belongs to a single cluster. What if I have a point right in the middle between 2 clusters? It probably was generated by one of the 2 clusters, but I don't really know which one. So it feels weird to say this is definitely part of this cluster, when in reality we're only 50% sure. That doesn't really make sense, so that's not great either. The other thing that you might have noticed on the previous slide is because we're going for Euclidean distance, it's basically a circle, right? So it's only looking for spherical clusters. In 2D, that's a circle. In 3D, that's a sphere. In n-dimensional space, that's a ball, I think is the mathematical term. But it's looking for balls. It's looking for spheres. So it only really works if your clusters are spherical. What if I have a case like this? This is what k-means is going to give me. It's got 3 clusters. As a human, I can look at that and see, well, I don't think those are right, right? It seems like there's squished ellipses, and it'd be better if it chose those. But because it's using Euclidean distance as a metric, they have to be spherical. Distance is always based on the diagonal distance. The other thing is that it assumes that all clusters are equally sized. So for instance, if I generate a bunch of random points from 3 different clusters, and they each have very different sizes, like the blue one is really small, the green one is much bigger, k-means is going to say, no, they're all the same size. Those are all just points from blue. When in reality, no, those are points from green. Green should be much bigger than it appears in this image. So that's another limitation of k-means. How can we solve these problems? Instead of learning a single cluster centroid, we can learn a Gaussian. We're still making the assumption that our data is Gaussian distributed, but we're saying in addition to a center, we also have a standard deviation. So that allows some clusters to be bigger than others. And instead of that standard deviation being a scalar, it can be a matrix. And that allows the standard deviation to be different in different directions. The other change that we'll make to k-means is that every point belongs to every cluster, but with a certain probability. So some, there's no way that this is from this cluster far away, very small probability. But others on the boundary, yeah, 50% this cluster, 50% that cluster. That makes perfect sense. And the result is that we get a much better classification for both of these different situations. You'll also notice that, for example, from the top right image to the bottom right image, the colors switched because the colors don't have meaning. We don't actually know what these clusters mean. We don't know what the labels are for these clusters. We just know that these points are very similar and they probably belong to one group. So that's the structure underlying the data. So this process is known as a Gaussian mixture model. It is a mixture of different Gaussian distributions. How do we initialize this? Actually, because k-means is so short and quick, we usually use k-means to initialize it. That's our starting centroids, and then we iterate from there. If you want to restrict it, I mentioned that it can learn diagonals because this standard deviation, this sigma, is a matrix. If I want it to be spherical, I can change my covariance matrix to be a diagonal matrix. And then all of a sudden, my clusters can have different sizes, but they're always a sphere. If I want them to always have the same size, I get rid of the matrix entirely, or I say everything on the diagonal is the same number, and then it basically goes back to k-means, but with probability. So what does this look like? I'll quickly iterate through a couple slides. Here is our starting position. Now notice that there's no hard clusters, there's just probability distributions. There's approximately 3 high values that correspond to where our initial k-means centroids might be. And as we iterate over the same process every time, we eventually get closer to a final solution where it learns 3 different probability distributions. Not just 3 clusters, but 3 probability distributions. These are 3 separate Gaussians, each with a different centroid, each with a different covariance matrix. So this is a more general form of k-means that tends to work much better, especially when you know that your clusters are not spherical or not all the same size. It's not perfect. It still has problems, right? So it's still making this Gaussian assumption. If you look at the images on the right, these are both quite common phenomena that occur in nature. On the left, well, that's what water looks like when you drop a little bit of water in a bathtub. It gets that ripple effect that goes outwards. If you wanted each ripple to be in one cluster, how would you do that? With k-means, it's not possible because we're, again, using distance. If I try with Gaussian mixture models, exact same problem, because there's not an underlying Gaussian distribution. There's no spheres, but there's also no Gaussians. But a human can do this quite easily. You say all these things that are close together are one cluster. All these things that are farther apart are a different cluster. Easy. So how do we encode that mathematically? Instead of learning exemplars, instead of learning centroids or Gaussians, we can play a game called Connect the Dots, right? So all the dots that are really close together, connect them, that's your cluster. Simple. This is what we are looking for in the end. These are better clusters. There are actually 2 different families of approaches to doing this kind of connect the dots hierarchical clustering. One is the agglomerative clustering. That's a bottom-up approach. You start out with n clusters. Every data point is a cluster. And then you say for every data point, what are the 2 that are closest together? Connect them. Now you've got n-1 clusters. Repeat. And stop wherever you feel like. So that's the agglomerative approach. There's also a divisive approach where you start with one giant cluster containing everything, and you say, what point is most dissimilar to my current cluster? Remove it. That's a new cluster. Repeat. So they don't always end up with the same solution, but they are both valid forms of clustering, and this is known as hierarchical clustering, and I'll show you why in a second. The other thing that I have mentioned a couple times is this k. With k nearest neighbors, we chose the k based on basically visual comparison. We said, oh, most of the time there's too much noise, so we'll use a bigger k. This seems okay. We didn't really have a mathematical way of defining that. With k-means, similar problem. If you can visualize this in 2D, great. You know how many clusters there are. There's maybe 4 or 5, but if you can visualize it, you don't need k-means at all. If you're in 10-dimensional hyperspace, you can't make a plot. You can't look at the data. So how do you know how many clusters there are? As with most things in machine learning, we try everything and we see what works best. So for k-means, for Gaussian mixture models, we use something called the elbow technique. And you'll need this on your homework assignment next week. So remember this for at least a week. On the left axis, this is our error. This is the amount of mistake that we're making. So if I only have one cluster, and I take the distance between every point in that cluster centroid, it's that value. If I have 2 clusters, then, well, okay, it's not so bad anymore. Maybe the error is halved because now there's 2 centroids. If we go 3, it gets even smaller. The error will always be greater than 0 until the number of clusters equals the number of points. But that doesn't mean that if there's 1 million humans, there's 1 million clusters. That's not useful, right? We want some sort of subset or category distribution. So we look for the elbow of the plot. At some point, it's going to stop decreasing significantly, and everything else is really just noise. It doesn't matter. So in this specific plot, k equals 4 is a very happy medium. It fits most of the data most of the time without too much error. If we add more clusters, it does get better. It does eventually look better, but you get diminishing returns. And if your ultimate goal is to try to classify things, to try to categorize things, great, you've got like 10 different categories and they're all basically dog or cat, but they're different kinds of dogs. Is that useful to you? It depends on your application. So this is how we choose k for k-means and Gaussian mixture models. How do we choose k for hierarchical clustering? I have an idea for you. Don't. And then you don't have to do anything, right? So when we do hierarchical clustering, we basically create this plot on the right, which is called a dendrogram. If you've ever taken biology and you've seen like a phylogenetic tree where like humans and apes are over here and birds are over here, etc., it's the exact same thing. So we take all of our data points, regardless of whether we're doing bottom up or top down, we look at the distance between all of our points and we say, oh, these 2 points are really, really close together. Let's merge them into one cluster. And then this point is also really close to this cluster, so we'll merge those into a bigger cluster. And then the next closest 2 points are these 2, so we'll merge these into another cluster. The y-axis here, this is the distance between the points in these 2 clusters. And we just keep merging them until we end up with one cluster at the very top. What I've done here is I've created a tree data structure that stores every possible value of k. And I can look at this later and I can say, for my specific application, I'm actually looking for the 3 biggest groups or the 5 biggest groups. And I can draw a little line, horizontal line through this plot anywhere I want, and I'll know what the groups are. I can also say, maybe going from the top down, 1 cluster is useless, I don't want that. 2 clusters, that's actually pretty good because they're quite different from each other. 3 versus 4, there's not really a big difference here. They're very close together, so that's not a good place to split it. But I can split at any line where there's a large gap of no change. And that is a pretty decent cluster to choose from. So this is how you could choose your k based on this plot. Now I keep using distance as a metric. There are many kinds of distance. You don't have to choose Euclidean distance. So for example, if we look at the plot on the right, let's say I get a new data point in green. I need to assign this to a cluster, either the orange cluster or the blue cluster. Which one is it going to be? If I use single linkage, I look for the nearest point. And I say the nearest point to here is right here. It's blue, therefore this is blue. Easy, done. But that's not my only option. I can also do average distance. So I can say, for this big blue cluster, the center is actually right here. And it's closer to here than it is to here. Actually, no, maybe this is a little bit closer. So it might go to this orange cluster all of a sudden. The second one is much closer to k-means. It's essentially a very similar algorithm. I can do complete linkage, where I say, what is the farthest point from this one for both clusters? So either this one way over here, maybe this one way over here. And whichever one is less far, then I'll put it in that cluster. So what that ends up changing is you end up with very spherical blobs compared to some of the other techniques. And there's all kinds of other ones. There's Ward, where you minimize variance. I have a whole plot of them here. Again, there's no correct answer. Depends on your data, depends on what you're trying to do with your data. As you can see here, for very different distributions of data, some of them are better than others. So if I've got those circles, or I've got those half moons, single linkage works really well because it's basically connect the dots. What's the nearest point? If I go to general clusters, it's awful, right? It just says these two green ones are pretty far apart. Everything else is the same giant cluster. That's not useful. But if I do something like complete linkage or word linkage, I actually get the clusters I want back out of it. If I've got those Gaussians, those long ellipses, first two don't really work very well. Actually, none of them really work very well. Use Gaussian mixture model instead. So there's different approaches for different data, but you can't always visualize your data. So you kind of just have to try all of them and minimize that sum of squared errors. The goal is that your centroids, your clusters, are a good fit for the data with as little distant values as possible. Now, I've shown you a lot of different models today, and your head is definitely spinning. And unfortunately for you, there's a lot more. What I want to focus on in this lecture and also in later lectures is not memorize these 100 different models and know exactly when to use them. My goal is that you kind of understand the broad families of models, the ideas behind them, why they work, why they don't work, and that you can refer to things like this to actually decide which ones to use in practice. So this is from the scikit-learn documentation. Scikit-learn is the machine learning library that everyone uses, which you'll be using on your homework this week. So you start at your starting point. Do you have more than or less than 50 samples? This is our decision tree, right? If you have less than 50 samples, you don't really have enough examples to learn from. You should get more data. If you've got more than 50 samples, are you predicting a category or a number? Okay, category, left side. Do you have labels? That's very important. If yes, great, you're in the family of classification. If no, we can still do clustering. If we're predicting a category, no, we're just predicting a number, great, that's regression. And if we're just trying to understand the data in a regression value, not a categorical value, then we could consider this something like dimensionality reduction. So that's things like manifolds. And then within each one of those, it really depends on how much data you have. So for example, support vector machines, support vector classifiers, these are great. These work really, really well, but they're slow. So if you have a lot of data, use a SGD classifier. We'll talk about this, but that's basically stochastic gradient descent. So you can kind of see the idea here. This usually tells you which model is the best to try first. Try the backup one too. So maybe it doesn't work and you try something else. And it works a little better, it depends on the data. But this is a cheat sheet that tells you where to start. Okay, we've got 20 minutes left. The last thing I want to cover is the coding side, so the platform side of this machine learning stuff. So if you're doing Python and you're doing data science, and there is a book on Python data science, if you're new to this, you've probably heard of these libraries. So there's NumPy, that's numerical Python, that's all of the low-level code for doing things like vectors, matrices, matrix multiplication. It's got a bunch of built-in things for those simple operations, and it rewrites all of them in C, C++, Fortran, so that they're as fast as possible, right? Really, really fast code for running these kind of simple array operations. Another one is SciPy. SciPy does actually have a lot of stuff for things like optimization. We won't be using SciPy too much in this course because there's other libraries that fill those gaps a little bit better. But if you wanted to mimic some of these libraries and do gradient descent by yourself, SciPy is a great place to start. Matplotlib, anything you need to do with plotting, it's probably Matplotlib. If you're using a different library, it's probably built on top of Matplotlib and just makes it simpler or easier to use. But Matplotlib is where all of the plotting tools in Python exist. If you want to make a plot, you use this. Most people start with those top three, and that's your usual data science course. You figured it out. At least that's how it was when I was learning data science. I think Pandas is a little bit more recent than these, but it's really popped off and exploded in popularity because it allows you to handle not just simple arrays, but tables, very similar to Excel. So now every column or every row has a name, and you can refer to it by its name, not just by its number. So there's much more powerful indexing. You can do things like time series analysis. You can do any pre-processing or grouping directly in a Pandas data structure. And then finally, scikit-learn. This is where all of the machine learning bits live. So the data, the models, pre-processing, cross-validation, metrics, etc. We're going to be using mostly scikit-learn for the first half of the course, and then mostly PyTorch for the second half of the course. And you'll see things like NumPy, Matplotlib, Pandas on and off every assignment. Anytime you need to make a plot, you have to go through Matplotlib. Homework 1, this week's homework I'll show in a minute. It's either NumPy or Pandas. I recommend Pandas, but if you don't know it and you're afraid of learning something new, you can technically use NumPy. So Pandas, preferably scikit-learn and Matplotlib. These have documentation. You can read the documentation. You should read the documentation. But they also have a lot of documentation. So what do I expect from you? Don't read everything. You'll never finish. I haven't read everything for these, and I've been doing this for 10 years. Know what these libraries are for. So like if you're doing something with arrays, you probably should be doing it in either NumPy or Pandas. If you're doing something with plotting, it's definitely Matplotlib. So know what they're capable of. This helps when you ask Google, Stack Overflow. You can technically ask ChatGPT, like, is there a function in Pandas that does this thing for me? But don't use it to write your code, please. And read the documentation as needed. So I actually want to quickly show one of these because I've had a lot of students in the past who said, it's not that I don't want to, I just don't know how to read documentation. It doesn't make sense to me. So I'll show some examples of documentation later when I show the homework. But these are things that you should know about and things that you will gradually learn over the next several homework assignments. Reading list. I found a bunch of tutorials that relate to the stuff in this lecture and are directly relevant for the homework assignment. These I actually do highly recommend reading. Most of them are relatively short. You can kind of skim them and get an idea. You don't have to read the whole thing. If you've never used Pandas before, the indexing is kind of complicated. NumPy, it's just like row, column, here's a number. But with Pandas, there's many different ways to do it. You can do row, column, number. You can do row, column, name. So if you're new to Pandas, definitely read this first. It will save you a ton of time. We're going to be doing a little bit of time series data. Pandas has a bunch of built-in stuff that makes time series easier. So also recommend this. Again, kind of long, but read the parts that seem like they are relevant. We're going to be doing linear regression with scikit-learn. Here is an entire documentation page on how to use linear regression with scikit-learn. Very useful. We're going to be doing linear regression on time series. They actually have a very specific tutorial for that. It's half of the first homework assignment. The other half is we're working with CO2 data, and they have an example that shows how to do that. So basically, if you combine all of these things, it kind of tells you what you need to do, but you need to figure out which parts of each of these are relevant to what we're working on. Again, don't read everything. You don't have to read anything at all if you don't want to, but read them as needed. They will help. They will save a lot of time. Feel free to email me and say, how do I do this? And I might say, read section 3 of this thing. Or I might say, oh, actually, that's a good question. It's not in these. Look at this thing instead. So please do email me if you need help with that. So what is our homework assignment for this week? I wanted to start, and I don't normally do this for every homework assignment, but I wanted to start off with some interesting history. So you probably know this person, especially if you're in engineering. He invented Fourier series, that thing that you hate, that you can't stand because it ruined your entire weekend that one year. So Jean-Baptiste Joseph Fourier, French mathematician, very famous. He didn't just invent Fourier series, he invented like a billion things. Like everything has his name on it. What a lot of people don't know, he discovered the greenhouse effect in 1824. So he sat down and he did what he's good at. He did math, and he said, wait a minute, the Earth is pretty warm, but given the approximate distance that we think we are from the sun, given the temperature of the sun, it's a little bit too warm. So something's going on here that we can't really explain. It's warmer than we would expect. You noticed this, 200 years ago? 202 years ago. Later, there was another American scientist, Eunice, political activist fighting for women's right to vote at that time. She was the first person to figure out the cause of the greenhouse effect. So she figured out that things like water vapor and CO2 actually trap heat, and that's why the Earth is warmer than we expect. She was also the first woman to publish a paper in a physics journal in 1856. So in 1856, we knew the cause of the greenhouse effect. Another person I love because he's got a great middle name, but also because no one believed him. He was an engineer, inventor, entrepreneur, basically made his own company, made his own business. And on the side, if that's not enough to keep you busy, he was an amateur meteorologist. And in 1938, he discovered global warming. He said, I've been taking observations of CO2 and temperature all over because I travel a lot for my job. And I've noticed that CO2 and temperature are both going up. And all of the scientists looked at him and said, what are you talking about? Like, that's not conservation of energy. That's not conservation of mass. How is that even possible? You're stupid. Also, you're not even a scientist. You're an amateur. So no one believed him at the time. But a small number of scientists did start listening. And they said, well, I don't trust his measurements, but I can also take measurements. Let's see if I can confirm or deny what he's saying. I just don't believe it. Another American scientist and also an alumni from my alma mater started taking observations at Mauna Loa Observatory in Hawaii. Started in March of 1958. Unfortunately, he passed away, I think, 5-10 years ago. But luckily, the science community continued to take these observations every hour of every day since March of 1958. And all of a sudden, we had unequivocal proof that CO2 and temperature are rising. And a lot of people have quoted this as one of the most important discoveries of the 20th century, all because of the people that came before him, but of course, him as the person doing the rigorous scientific study of this. His name is Charles Keeling, and he is known for the Keeling curve. So I'm going to show this in a second. Before I forget, next week, next lecture, I'm going to be talking about data sources. How do you find satellite imagery? How do you download satellite imagery? How do you work with satellite imagery? It is very helpful if you bring your laptop to do the same thing at me at the same time. It helps with learning. So try to remember to bring your laptops next week. If not, it's recorded and you can rewatch it later, but it is nice to be able to follow along. So let's look at the Keeling curve. How many of you have heard of the Keeling curve or seen the Keeling curve before? This is what happens. So my bachelor's was in geology. My bachelor's was in earth science. So this was like every day of my life. And then as soon as you get out of that, you realize like, oh, right, normal people don't know what this is. But I get excited about it. So this is the Keeling curve. If I go to 1 week, these are the observations recorded in the last week, ending April 17th. So they're only a few days old. You've got a measurement every hour. It's kind of noisy, there's ups and downs, and you've got an average every day. If I go to 1 month, there's more noise, but if I look at the weekly averages, it's relatively smooth. If I go to 6 months, some wiggles, but it's pretty constant. But something weird happens when I go to 1 year or I go to 2 years. You start seeing this sinusoidal pattern. These are measurements of CO2. Why would CO2 be going up and down every year, once per year? Winter. Whose winter?
Our winter, because when our trees don't have leaves, but the Amazon rainforest does, that kind of thing.
Yeah, so this is a really good point. So when trees grow leaves, they suck up CO2. When they drop those leaves and those leaves die, they release CO2. There's 2 winters. There's the northern hemisphere winter and the southern hemisphere winter. This follows the northern hemisphere winter because the northern hemisphere has more land surface. The southern hemisphere is mostly ocean or Antarctica, which doesn't have trees. So, and Hawaii is also in the northern hemisphere, so that could also be linked. But what you see is that in the spring, you get this gradual increase. Okay, yeah, here it is. So plants drop their leaves in the fall, and the leaves start decaying. And as they decay, they release more and more CO2. And then by late spring, early summer, all of the trees have new leaves, and they start sucking up CO2. And so this stops and eventually starts going down. And the cycle repeats. So that's the annual cycle. There's an annual sinusoidal cycle. Unfortunately, that's not the only cycle. You'll notice that the right side is a little bit higher than the left side. This is only for 2 years. If we look at the last, 70 years? It looks something like this. So this is why it's called the Keeling curve. There's a quite rapid rise in CO2 levels. Now, I remember when I was an undergrad, people kept talking about 420 is the limit. If we go over 420 parts per million CO2 in the atmosphere, there's no saving us. And then people started saying, well, actually, maybe 430 is the tipping point. Maybe 440 is the tipping point. We keep pushing it, but the fact of the matter is the CO2 keeps going up. And as we saw from Eunice, we know that if CO2 goes up, temperature also goes up because of the greenhouse effect. This is the observations at Mauna Loa. We can also go back further by looking at observations in other places around the world from older, less accurate sensors. But we have some observations for a couple hundred years. People have been studying this for a while. So this is the last 300 years. And you'll notice things have been slowly increasing since the start of the Industrial Revolution, but they've really started to speed up recently. If we go back 2,000 years, now we're starting to use proxy data. So there wasn't someone 2,000 years ago measuring the parts per million of CO2 in the atmosphere, but we can look at tree ring growth, we can look at bubbles in ice in the Arctic or Antarctic, and see what the CO2 levels were back then. And you can see it was relatively stable, and then there's this giant hockey stick curve at the end that's known as the Keeling curve. If we go back 10,000 years, it gets worse. So this is not great, right? It's very rapidly increasing all of a sudden. If we go back 800,000 years, there are ups and downs in the past, but this is by far steeper than anything that has ever been recorded. If we go back 70 million years, there actually have been times in Earth's history where CO2 was higher than it is now, where there are no glaciers, there are no ice caps, there's no Antarctica, and everything is melted. But the point is that things are changing so rapidly that it's not the magnitude, it's the acceleration that's the problem. Species cannot evolve quickly enough to adapt to these increasing CO2 and temperature. So that is the motivation for the homework assignment. What are we doing for the homework assignment? So this is up on Moodle. You can download this. This is homework 1. We're going to be doing regression. A couple points for all the homework assignments. You're going to download this Jupyter Notebook, and then you're going to type into Jupyter Notebook, and you're going to run it. And then you're going to upload the same notebook so that I can grade it. So please don't upload a PDF or a .py file or a Word document or whatever else notebook. And also run your code and save it. For some of the homeworks, I'm actually going to run it to make sure you're not lying and pretending that you got these results. But for others, it takes me a long time to do that for every student. So it helps if I can see your plots without running it. So those are 2 points, and that's true for every homework. Here is our Keeling curve, CO2 levels. I think this is up to date, but maybe this is an older image. Okay, this is another really important point. So for each homework assignment, these are the things that you're allowed to use. Please don't import other stuff, because there's a lot of stuff that I'm going to teach you later that I don't want you using on the first homework because it makes it trivial. So you're allowed to use anything in NumPy, anything in Pandas, anything in Matplotlib, also anything in scikit-learn. So I'm specifically importing fetch OpenML and linear regression because I think these might be very helpful for you. But you're allowed to use anything in scikit-learn, not just these 2 things. Is that clear? And then you can import like built-in Python stuff like OS or sys or math, but don't import anything else that isn't part of Python or one of these libraries. Otherwise, you'll lose a few points. These are the imports that I used in my solutions. Hint, they may be very helpful to you. Pandas might have some very useful functions that are very useful for specific parts of this homework assignment. If you would like to fetch machine learning data for use in scikit-learn, there might be a function that is very useful for that. And similarly, if you would like to do linear regression, there's really only one way to do it. You don't have another choice here. So these are all very useful to you. Do read the documentation for these. I'll show you one of them in a second. Step 1, download the Mauna Loa CO2 dataset. This is the Keeling curve. Download it from OpenML. If only there was an easy way to quickly fetch data from this website. I say this, and yet every semester someone finds other ways to do this that don't involve that function. But this is very easy to do. Use it. You can use NumPy or Pandas. Like I said, Pandas is better. It's a little bit more complicated, but it is worth learning, and this is a good chance to get used to it. Familiarize yourself with the columns, units. You can just like print the thing and see what's inside. Don't worry too much about the details of that. Step 2, pre-processing. So we've got some dates in our data set. We've got year, month, day, columns. You want to combine those into one date time. So Python has a date time format, NumPy has a date time format, Pandas has a date time format. Using that, compute the day of the year, so like 1 to 365, and then compute sine and cosine of day of year, because we expect to see a sinusoidal pattern. Hint, the sine and cosine functions in NumPy and Pandas, they assume things are in radians, so you need to convert them to radians. Another thing that students always get stuck here is people are really worried about leap days. Some years have 365 days, others have 366. What will I do? It doesn't matter. They're basically the same number. They're only off by a small amount. We're engineers. It's all the same thing. We're not mathematicians. So don't worry too much about that. Training, you're going to train 3 different linear regression models. One is just date time. So here you need to convert your date to a number, but if you scroll up, there's ways to do that quite easily. One is the date time and the day of year. So now you have 2 inputs, x1 and x2. And then the third one is date time, sine of day of year, and cosine of day of year. For all 3 of these models, train it, fit it to your data that I give you, and then use it to make a prediction of the future. Remember, we're learning a linear function with or without squiggles in it. If I give you a new x, you should be able to give me a new y with your machine learning model. Plot these things. So basically remake this plot. Again, don't spend like 2 hours adding the perfect blue shading. It doesn't matter. I just want to see like the lines. You're going to find that the data that you download is basically like from 1958 until like, I don't know, 2005, 2006. You're going to plot the past data. And then you're going to use your models to make predictions of future data. Basically 2005 until 2026. Put them all on one big plot. The other thing that's really important, please, please, please add titles, axes, labels, units, legend to your plot. This plot has great labels. Look at this, CO2 concentration, parts per million, title, very useful. So please add these things. You will lose a little bit of points if you miss them. The plot is pretty big and the details are kind of small. So feel free to zoom in the plot, depending on what version of Matplotlib you're using, you might be able to zoom in. You can also set the limits of the axes to be smaller, whatever. You can also squint, you can get out the magnifying glass. And then after you've got your predictions, I want you to answer these questions. Just one sentence, it doesn't need to be very detailed. Basically, you've got a date time model, you've also got a date time and day of year model. What's the difference? Why? Same thing for sine and cosine. What happens when you train a model on sine and cosine? This is another place where people get stuck. You don't have to do any fancy machine learning evaluation stuff. I haven't taught it to you. That's the evaluation lecture in a few weeks. For now, which one looks plausible? Which one makes sense to you? Using this model, what is the predicted CO2 for today? How does this compare to the actual CO2? Just put those in there. That's the whole homework assignment. You will find that if you're not used to coding every day, this is going to be really boring and tedious. I promise it's not a waste of your time. You will learn a lot by doing it, and all of the later homework assignments are going to feel much easier. But because this is the first time you've coded a lot of this stuff by hand in a while, it might feel tedious. So that's the homework assignment. For every homework assignment, I like to have extra credit. This is the extra credit. So you can get over 100. If you miss points on a later assignment, this might make up for it. So you've got a linear model. You've got a linear model with a smaller linear trend for day of year. You've also got a linear model plus a sinusoid for that annual trend. Unfortunately, CO2 is increasing exponentially. So humans have seen the cliff at the end ahead of us, and instead of slamming on the brakes, or instead of coasting to a halt, we've stepped on the gas pedal. We've said, let's see how fast we can go, and CO2 is still increasing exponentially. So for extra credit, try to fit an exponential trend to the data. The only hint that I'll give you, I try not to give too many hints on extra credit. The only hint I will say is if you sit down and do the math by hand on pen and paper first, the code is really easy. But if you just try to code based on like, oh, it's probably something like this, it's probably not going to work. So try to do the math. Basically, you have an exponent on one side, you take the log on both sides, and then now it's an easier to fit thing. So that's the extra credit. And then I promised that I would show what documentation looks like. So let's look at pandas to date time. Okay. So these are the API docs for pandas. It has this built-in to date time function. It takes an argument. That argument is an int, float, string, date, time, whatever. That's the type of the argument, and it has a description. Everything else is optional because it's got a default value. This is the default value. That's the default value. These all have different types, different accepted values. So this is what Python documentation usually looks like. I don't see anything else that looks weird. When you see something like this with angle brackets, that doesn't mean you type the angle bracket. But when you see something like this, that means you do type the string character. So that also sometimes confuses people. This means either one of these two from this set, not both of them in a set. Any Boolean, true or false, but by default it's false. Yep. So hopefully this isn't too awful, but I do know that it's much less common for people to read documentation because of ChatGPT. So I want to make sure people remember how to read documentation. It is quite useful. So I do really recommend looking up the documentation for at least these things because I use them to solve the homework, so it might save you a lot of time. The rest of the stuff, something in Matplotlib, something in Pandas, I think that you'll figure it out. It's not too hard, but that's my hint for you. Any questions on machine learning, homework, anything else? Went a little bit over time, so apologies for that. All right, then I will see you all next week. Remember to bring your laptops so that we can follow along with data downloading.